All right, so we are going to do an extension of what we had learned initially, which is an extension of the t-test. It's called ANOVA, analysis of variance. I just want to explain to you when you use analysis of variance and how it relates to the t-test. So to do this, I just want to get the ANOVA data, the data that I just made to help with analysis of variance. So, like I said last time, you would see that when you just import your Stata file, it will have the variables showing in here. The patient ID, estimated glomerular filtration rate, is at baseline, and estimated glomerular filtration rate after treatment, the difference between the baseline and after treatment, the sex, the toxicity, and the treatment. So if you want to see what this looks like, more like an Excel sheet, this is what it looks like. Now, we talked about the fact that when you're dealing with statistical tests, you are going to have different kinds of statistical tests. Some of the statistical tests are actually going to be referred to as parametric tests, and the parametric tests would most often be based on the mean. And we took time to explain why it's undesirable for you to use the mean as a measure of central tendency, especially because the fact that when you use the mean is going to be affected by the outliers. So you don't necessarily want to use the mean if you have extreme values. And you want to use the median instead, because the median is based on ranked correlation and would not be affected by presence of outliers, and it's also not going to be affected by a very small sample size. It won't be as affected much. But when it comes to the mean, if your sample size reduces, the effects that one observation has on the mean actually increases. We also went on to do an example where we were able to show that if the sample size increases, the effect of one observation on the mean reduces. We actually gave an example of getting 3,000 children aged 3 years and then added an 8-year-old man, and we're able to show that the mean still remained at 3. Remember that example? Great. So at this point in time, I just want to show you the data, what it's going to look like when you can use ANOVA. The last time I showed you when you can use the t-test. There were 2 types of t-tests that we talked about. We said there is what we called the independent sample t-test, which is the unpaired t-test, and then we also had what we called the paired t-test. We said you want to use the t-test to determine whether there is a difference between 2 means. And for instance, you can actually use the t-test to determine whether there is a difference in the mean EGFR here between maybe the males and the females. So there are 2 groups, so you want to determine the difference between 2 means. The now hypothesis of the t-test is that there is no difference between 2 means. You ought to remember every time that to use the mean, you have to be very sure that this variable you're dealing with is normally distributed. So, just as a quick demonstration, what we had done, we said you can actually do a t-test. Say t-test estimated glomerular filtration rate by sex. Okay. T-test EGFR1. 6. What is happening? Oh, okay. Test EGFR1 by 6. And you would see that it is actually going to give you the difference between two means. If you check here, it's saying the difference between the mean of the females and the mean of the males. It goes on to actually calculate your means. It tells you that you have 120 females and 83 males. Then it gives you the mean there. The mean for the females was 123. The mean for the males was 129. This is the standard error, which is actually calculated from the standard deviation divided by the square root of sample size, which is the square root of 120 there and the square root of 83 there. Then that's the standard deviation that was divided, and you have your confidence interval there. We said you have two ways in which you can make a decision whether there is a statistically significant difference. One way, we said, is by simply looking at the p-value. And p-value just gives you the strength of evidence that you have to reject the null hypothesis. If the p-value is less than 0.05, you actually have strong evidence against the null hypothesis. The null hypothesis, we said, is stating that there is no difference between the two means. So if the p-value here were less than 0.05, we could have had enough evidence to say there was a statistically significant difference between the mean EGFR of the females and the mean EGFR of the males. The other way, we said you can actually use the confidence interval. And we said if the confidence interval of the difference actually has the null value in between it, as is the case here, starting from the lower quartile, lower confidence limit having -16, the upper confidence limit having positive 3.5, from -16 to 3.5, the null value 0 is there. So we know that there is a possibility of observing 0 in the difference between these two means, and therefore there is not a statistically significant difference. We also went on to use these two, and we said that if these two confidence limits actually overlap, you would actually notice that there is not a statistically significant difference. So here you are. You've seen that there is not a statistically significant difference here. Now, we also went on to say that one of the crucial things you have to do is make sure that the assumptions of the t-test have been met. And to make sure of that, you have to check the distribution of the variable you are interested in. In this case, the variable EGFR ought to be normally distributed if you're going to use the t-test. So we said you can use histograms, EGFR1, and it's actually going to give you a graph that will show you how the variable EGFR1 is distributed. This is a bit slow because it's running few other heavy stuff, but yeah, here it is. One here might still see a normal distribution even if it is not there. So histograms could be something that can help you see what the distribution is like. This is an objective way of doing it, because one could choose to see a normal distribution where there is no normal distribution. Therefore, you have to use a statistical test to test the null hypothesis that the distribution of the variable does not deviate from the normal distribution. That is Shapiro-Wilk test. There are a number of them, as I had already mentioned. But the Shapiro-Wilk is an easy one. Shapiro-Wilk test, you say S-Wilk EGFR1, and it will give you p-value here. The null hypothesis of this statistical test is that the distribution of the variable, it does not deviate significantly from the normal distribution. If the p-value is less than 0.05, reject the null hypothesis. So here, the p-value is less than 0.05. You have strong evidence against the null hypothesis that the distribution of the variable does not deviate from the normal distribution. And this is just saying the variable is not normally distributed. Therefore, you are likely to make errors if you actually applied normal distribution assumptions to a variable that is not normally distributed. Remember that example we had given where you had an old man in class and you were able to make the wrong conclusion there. So what do you do in this case? You use the alternative of the t-test, which is the non-parametric alternative. We call it the Wilcoxon's rank sum test. So we say rank sum EGFR1 by sex, and this is not supposed to be happening. Yes, sex. And it actually gives you a p-value of 0.64. So this is still telling you that there was not a statistically significant difference in the estimated glomerular filtration rate of the participants before they started treatment. This is desirable because it means that the way we had collected the participants was random, and it means that these two groups were very comparable. Interestingly, if you did the same command on the EGFR4, you are likely to see a difference. This is because the drug these patients were put on had ended up causing nephrotoxicity, which reduced their kidney function. So if, for instance, you try to do a t-test, which we said is not desirable, and you just change to EGFR4, the EGFR after treatment, the command is going to still remain the same. It will show you that there was, interesting. It tells you that there was not a statistically significant difference as well between the males and the females, which is good. Okay? However, you cannot rely on the t-test. In this case, you have to use the rank sum test. It tells you there was not a difference between the males and the females, which is interesting. Now, let's say you want to compare the patients that ended up with nephrotoxicity and those that did not end up with nephrotoxicity. What result are you going to get? So, nephrotoxicity, the variable here, is also a binary variable. So you can actually do the same command we did, t-test, EGFR1 by nephrotoxicity. So basically what you're saying here is, was there a statistically significant difference in the estimated glomerular filtration rate of the participants that ended up with nephrotoxicity and those that did not end up with nephrotoxicity at the time when they were beginning treatment? This is the question here. And when you check, it's telling you from the t-test that there was not a statistically significant difference. And if you check the confidence interval, it's actually having a 0 in between there. This is using a t-test. So you know that the variable EGFR is not normally distributed. You don't want to use the t-test. You want to use the Wilcoxon rank sum test. So you say rank sum EGFR1